Okay, we are RBs Group 1. This is me, Emiliano Jofre from Argentina, Richard Hart from UK, Romina Petrucci also from Argentina, and Suguru Rio from Japan. And we studied the effect of planetary period on planet detectability. Our project goal was to investigate if it's easier to detect short or long period planets with the radial velocity technique considering the same amplitude. And our hypothesis is that shorter period planets might be easier to detect than longer period planets, since mainly because you can record many more full orbits, and also you can get stronger RB signal for a given mass. And on the other hand, you could get higher probabilities for transit follow-up.
Okay, so this is the methodology that we chose to follow when modeling a single planet and a star. So first off, we modeled some random stellar RV signals. So this is just a time series of RV data generated from Xavier's SOAP code that he talked about earlier in the week. And then we injected a planet where we can choose the amplitude and the period. And then we take 20% of this RV data and we move it across into a validation set. And we remain with the 80%, we focus on the GP and the MCMC. And then we can put the 20% back on and see if it overlaps onto the fits. And then we know our fit was appropriate. And the model we choose to fit is a Keplerian model with a single star and a single planet. And we see whether it's more likely that that model fits or whether there's no planet. So just a quick word on the stellar variability. You can see in the top right, that's just the pure RV stellar noise sources. So you can see there's some like large amplitude, quite short period oscillations ranging from plus or minus 10 meters per second. And then in the top right, you can see we've subtracted a lot of that data. So we've just chosen one data point per day. And we've reduced it again by 30% for instrument downtime and bad weather. And then in the bottom left, you can see the red crosses represent the randomly selected 20% that's moved across into the validation set, and the black circles are the training set. And then we fit a GP shown by the green in the bottom right to show that the GP can fit. So these are the planets we just chose to kind of arbitrarily to fit. So there's two planets, a high amplitude and a low amplitude. So the high amplitude could be a gas giant, and we put it at either 2 days or 100 days, and then the low amplitude is like a super Earth or something, and we put that again at 2 and 100 days, and we compare the results. So here's just a quick sort of preview of the GPs and the MCMCs in action. This is just 25 randomly selected 25 results of the MCMC in the green. You can see it trying to fit the planet parameters, and then the black line is the GP trying to see if those 25 fit. In reality, I think we did about 1,500 MCMC walks, but we just showed a selection set here. So.
Well, I'll show you the results we have obtained. First, we investigate what happens if we have a high amplitude planet. So we suppose an RB amplitude of 20 meters per second. We choose two different orbital periods, one of 2.2 days and the other one of 100 days. Here, the blue histogram corresponds to the Gaussian process model only, and the green one corresponds to the Gaussian process plus planet model. So in both cases, we were able to detect the planetary signals, but as you can see here, the separation between the histograms is larger than the separation between those other two histograms. So we conclude that short period planets are easier to detect. The reason for this is that when we have short period planets, we have a better phase coverage. So well, that's our first result. Then we try with a low amplitude planet, specifically an Earth-like planet. So we suppose an RB amplitude of 2 meters per second. We choose again the orbital periods of 2.2 days and 100 days. Here we also conclude that short period planets are easier to detect, but the results are not conclusive because, as you can see, the histograms are quite overlapped. And finally, we try with a very low amplitude planet. We suppose an RB amplitude of 0.5 meters per second and a period of 2.2 days. Well, the histograms are almost fully overlapped, so our general conclusions are that we have no chance to detect very low amplitude planets or Earth-like planets.
Okay, and this is our conclusion. This shorter or hypothesis, shorter period planets are easier to detect is right, and we should check the more variable periods to fit, and we should check to fit the data, and we found that through ways to improve the detectability. The one is we should do more intense observations to trace the stellar activity and and the second one is we should do the longer observation run to detect the longer period planet. And the last one is we should target the Roma stars because in Roma stars the amplitude increase in the Roma stars, the semi amplitude because increase. And that's all. Thank you. Yeah, it's true, but we don't think the stellar activity in the Roma star.
Yeah, we said that we wanted to target lower mass stars because the mass ratio for a planet to a star is high, so you have a higher amplitude for a low mass planet and a low mass star. But the question was, do low mass stars have different or more activity? And the answer is yes, they do. But this is under the assumption of a given stellar activity model. You know, what can we then infer from that? Obviously, you'd use a different model for an M dwarf or something, which we haven't done.
Good afternoon, everybody. We did our project on something similar to what the previous group did, but instead we're looking at the effect of planetary amplitude on the planet detectability. My name is John, and then here's Jing. We got Mateo and Jorge right here. Okay, forward. Okay, so our project goal was basically to use GP regression modeling to try and see if we can detect a planet that is orbiting around a sun-like star with a circular orbit with a period of about 10 days, and also the star that the planet is orbiting around is near the solar maximum. So we wanted to see, is it easier to see lower mass, or investigate, is it difficult to see smaller amplitude signals or large amplitude signals? And then what is the actual threshold amplitude for each detection?
So our hypothesis is that larger mass planets should be easier to detect than smaller mass planets because larger mass planets will cause a larger amplitude in the RV data. And for our method, we just fix all the other parameters except for the radial velocity amplitude. And we change the radial velocity amplitude from 0 meter per second to 10 meter per second. And then we run our MCMC on the Gaussian process regression model and compare the model with only Gaussian process or Gaussian process plus a planet signal.
Okay, our first test to see our basic hypothesis if larger or smaller amplitude planets were easier to detect was of course to look at the periodograms of the radial velocity time series. And as we can see, there are two main, the red line is the period of the planet that we injected in the time series, which is 10.2 days. And we can see also the 25 peak of the stellar activity, which is the stellar rotation, which is really strong, of course, in the left plot, in which the planet has only an amplitude of 10 centimeters per second, but on the other extreme case, we examined for a 10 meter per second planet, we can see that that is still present at 25 days, the stellar activity signal, but the planetary signal is much more stronger. So we are already prepared to confirm that higher amplitude planets are easier to detect. Please.
As we can clearly see here, with a really low amplitude, like 10 centimeters per second, we cannot see any model with a really great likelihood or evidence against or in favor of them. But when we are increasing the amplitude of the exoplanet injected in our signal, the evidence is going farther from one to each other. For example, in 10 meters per second amplitude, we can infer that the Gaussian process, the stellar activity plus planet is preferable a model, but and with an amplitude, this is the threshold amplitude that we were talking before, is of 4 and 25 meters per second. We can distinguish clearly which model is more favorable. And of course, the higher we go, the evidence is much more better.
So we ran mini amplitudes than what we just shown on the previous slide, and this is just a plot showing all of the runs that we looked at. So here's the K amplitudes here on the bottom, and then on the x-axis we have the evidence, but also the log of the evidence here on this side. The corresponding planet mass is up on the top axis as well. One thing that we learned was that an evidence of around 100 is good enough to say a confirmed planet. And so looking at where 100 was, that kind of corresponds to a K amplitude of 3.75 meters per second, which is about 13-ish Earth masses. And we could kind of see that the trend in the evidence kind of goes exactly the way that we expect it to.
Okay, and one thing that we found, and it wasn't expected, is that in average we have found a kind of bias from the expected value. I mean the input value and the results. As you can see, the vertical red lines shows the amplitude that we have input, and in most of cases, as we can see, there is a 1 meter per second bias. We were also with the zero amplitude. I mean, we make that experiment, and it supposes there is this, and there should be no planet, no amplitude. So we start suspecting that probably the prior that we have used for the amplitude is not really uninformative. So probably there is a kind of problem with the parameterization of this uninformative prior. But also we cannot say that all of data. I mean, if when the evidence is not really good, any results can be possible. For example, in the K equal 2 meters per second, we can see that the bias is in the opposite direction. So if we don't have enough evidence, we cannot say anything properly.
And so, as for the conclusion of our work, we of course find that larger amplitude planets are easy to detect, and we detected that the detection limit for our configuration is 4.75 meters per second. And also we observed this amplitude bias in the MCMC code, which is possibly caused by the uninformative prior that we use that are not so uninformative, or also because we were forcing the MCMC code to find a periodicity between 9 and 11 days, and thus we were forcing it to find a planet periodicity in the data, which he found even if it wasn't there. Of course, this test is not conclusive because we tested just a simple a small sample of data. A way to improve this test is, of course, to combine our work and the work of the previous group and test all over the period amplitude space to see where is the threshold between the detectability threshold. And of course, we used only one configuration of stellar activity, one stellar spot configuration. So another possible change is to study different type of stellar activity, different number of spots, so different spot plage ratio or other possible effect to have a more robust and significant result. Thank you for the attention. Yeah, so the question is if the bias in the amplitude recovery is due to the amplitude to the planetary model absorbing part of the stellar activity, and I think that this is definitely the case. Also because we have a 10.2 days orbital period, which is not that far from half of the rotational period of the star. So there can be some exchange of signal between the two of them. So yes, the answer is yes. I think the same is the case. Thank you.
Thank you very much.
Okay, hi everyone. So I am Umberto, he is Jacob, and she's Jessica. And our talk is about the impact of a changement on the stellar inclination on the system. And only to be clear, with stellar inclination it means that we are maintaining fixed the inclination between the orbital plane and the scale of the plane, so the planet is only in the position when the radial velocity is changing. For us, we are only changing the inclination of the star, and we want to understand how the differences are, if there are differences between the classical case in which the inclination is of 90 degrees, and we want to decrease this value until 0 in order to understand if there are differences. So we have to answer on these two questions mainly. The first one is only relative on the impact on a spot or a plage presence, and the second one is the impact if we add a planet. Sorry?
You're echoing.
Is it? Can you hear me? Okay. Sorry. And these are our initial hypotheses. But can you hear me? Okay, because I cannot hear me. Okay. But in our initial hypothesis, in which obviously if you are going to decrease our stellar inclination, what we expect is that also the effect of a spot of a plage is less revelable in our RV analysis. And on the other hand, we have a positive impact in a sense that if there is a planet, we can easier identify it. So that's our initial guesses. And now we are going to do the analysis.
So while our ultimate goal is to figure out how the stellar inclination affects the ability to detect a planet, we first needed to isolate how the stellar inclination actually just specifically affected the RV activity signal that we picked up. So we used the SOAP2 toolbox that we were given and basically changed the inclination of our system, starting off where we're pointing at the equator of the system until we're eventually looking at from a pole-on perspective, as you can see here. So our first result, and this was just with one spot plage system, so no planets were injected in here. We can just isolate the effect of here. Might be a little bit difficult to see, but at the top, there's basically two plots associated with each inclination, and here we go from 90 degrees, which we've assigned to be equator on, down to 0 degrees, which is pole on. It starts off with a nominal flux at 1 until eventually we can see we're decreasing to a negative nominal flux, or sorry, slightly less than 1 nominal flux, whereas our radial velocity also has that downward trend. So you can see that as our inclination changes here, the effect of the spot blocking out the blue shift, red shift from the relative rotation decreases, whereas the convective blue shift still remains prominent in the whole system. So to talk about how this actually impacts as we scale up the project to look at the detection of planets, I'll let Jennifer handle that.
Thank you. All right, where are we here? Ooh, they're labeled. All right, first I'm going to talk about looking at the effect of the inclination on the stellar activity itself. And here we can see the stellar activity, the active regions only really depend on the latitude, and that doesn't really change with your view of the inclination. And the number of spots and their coverage also doesn't depend on your inclination. What you see eventually will, but the first part of the model only really considers where they are on the star. And here is where it gets a little interesting. We start seeing that the correlations between, I've only shown the spot plage, end plage correlations, and you see that at first we kind of have this wide spread out structure in our corner plot, and for 90 degrees, which is again equator on, and as we get to 30 degrees, we start seeing more ridge type structures. And the final effect of this is that for the observed flux and radial velocity from our noise source, spots and plages, is much greater for your 90-degree inclination than it is for 30-degree inclinations. So what are our results? Of course, as the stellar inclination approaches zero, pole on, the structure of the correlations do change, and we also see that there's a decrease in the magnitude of the RV signal from just our noise source. Finally, I'm going to talk to about how this actually affects planet detectability. So our stellar parameters are all kept constant, basically sun-like, except for the inclination of the actual star. The inclination of the planet stays constant at edge on, and we're dealing with an RV semi-amplitude of roughly 3 and a period of roughly 10 days. So first off, how does this compare for actual magnitudes? Here, let's see. We see our 90 degrees, 60 degrees, 45 degrees, and 30 degrees. And as the inclination slowly decreases, you can see that the scale changes such that the signal in black from the star decreases, but we still have that same signal strength from our planet. Excuse me. Looking at our parameter set, we see that this side shows the semi-amplitude, where this side shows I can't read it, period. The period. And the main point to see here is that it always stays roughly centered at the same points, but as the inclination of the star decreases, the width decreases. This allows us to it basically reduces our error bars. Finally, let's look at the log evidence. And as inclination decreases, the separation between our peaks increases. So not only do we get better characterization, we get better detection as well. And is this where I hand it over to you? Yeah.
So just to basically sum up what we were talking about before, our major results is that as the host star is viewed more pole on, as we avoid the motion around the star and more have it just stay in the same plane, we can more easily detect the planet. So this reflects our initial conclusion. As you can see here, we've also plotted the relative log evidence, starting with an inclination. The smaller the inclination, the closer to pole on, and you can see a steady decrease in trend here. Unfortunately, we had issues as we brought it closer to exactly 0 degrees inclination, which leads me to our first major point that we'd like to do if we were to improve this in the future, which would be to exactly examine it at the pole-on situation, just because we had issues running that in the code. The next thing we'd like to do is we understand that this is not necessarily representative of a true system. Oftentimes, stars and their planets orbit within the same plane. The rotation of the star and the equatorial plane are the same. Here we only varied the inclination of the star, not the orbit of the planet. So we'd like to go ahead and maybe examine changing the plane as well, because as we've seen, while an edge-on case is ideal for detecting the planet, the pole-on case is ideal for minimizing the impact of the stellar activity. So perhaps there might be some sort of sweet spot somewhere in the middle that is the ideal location for detecting a planet in a real system. Finally, different types of stars, different types of planets might also improve this analysis. So with that, I think we'd like to open it up to any questions.
In this case, the planet is always edge on to our line of sight. In this case, let's see, I'm not sure if it's faster. I thought about adding like a linear fit to this plot, but I wasn't really happy without doing it without any real analysis behind it. Linear fit roughly looked better on Excel, but then the exponential fit, but again, I wasn't really comfortable putting any numbers to it. We have to move to the next group, I'm sorry.
Hi, everybody. We are the J's, where the S is for Sarah, and the rest of us are Julian, Jonathan, Jason, and Joe. And the question we were put was to look at how the stellar rotation period affects your ability to detect a planet. So we have two sets of questions. The first set of questions really have to do with the sources of astrophysical noise that we're trying to separate out from the planet signal. So first is the general amplitude of the RV signal, the effects of the spots and the plages, and then the third part of the astrophysical signal set of questions had to do with the way we measure things, which is really the Gaussian shape of a spectral absorption line, and the ways we quantify the properties of this and how these are affected by the rotation period. So this is the bisector span, the full width F-max, and the depth of the absorption. Finally, after we can understand where our noise is coming from, we get to the point, which is to actually perform planetary detections. So we formulated hypotheses to test. So to the first part is the activity RV signal. Sorry, this is the stellar activity induced change in the RV amplitude that we measure. We said that it will increase with increasing rotation period. Faster stars are noisier. They generate more magnetic fields, which create spots and plages. We decided that the net blue shift of the bright plages would have more of an effect than the spots. And as far as the correlations go, we decided that they would increase as the stars spun up faster. I would be happy to tell you why we thought that, but I would deprive you of the pleasure of figuring it out for yourself. But in the end, we decided that since slower rotating stars are noisier, we would do better luck with slower rotating stars. And now I'll hand it over to Julian, who will talk you through our methods.
So I kind of lost my name tag, but I'm still Julian. So as far as methodology, we were doing basically the same thing as all the other groups you've been seeing so far, but this time we're keeping everything the same except for the stellar rotation period. I should say keep all parameters, I guess, except stellar rotation period the same. Which end is a laser pointer? Oh, the bottom one. There we go. So we injected a planet with a 5 meter per second signal into our data. We chose 5 meters per second because that's about the same level as the stellar variability that we were expecting. And we're trying to see if we can extract that planet signal from the stellar variability. So if we had a planet signal that was much bigger than the stellar variability, you'd expect to see it all the time anyway, right? And we kind of arbitrarily chose a period of 23 days. And then for the planet's orbital period. And then for the stellar rotation period, we chose 5 meters per second for a short period. And then 11.5, which is exactly half the rotation period, orbital period of the planet, to see if there's any aliasing issues that we might run into. 25, which is close to the planet period, 30, which is intermediately far from the planet period, and then 40 days, which is a long period sample. And then, so first result is the effect of the stellar rotation period on the radial velocity you measured due to the stellar activity. So first off here you can see the overall level is of the order of 5 meters a second, which is similar again to our radial velocity semi-amplitude from the planet orbit. And you can see this overall trend going from high stellar activity at fast stellar rotation to low radial velocity induced, sorry, let me get that right, low activity-induced radial velocity signals at slow stellar rotation, and that kind of intuitively makes sense. Like if your star is not rotating at all, it's just sitting there. Maybe you've got some spots on the front, but nothing's happening, so you're not going to expect to see any variability in the radial velocities. If it's rotating very fast, then you've got spots at your approaching and receding limbs, and as it goes faster, those are approaching and receding faster, and so you expect a bigger signal. So that kind of makes sense. So yeah, we're keeping the number of stars fixed for all our rotation periods. Yeah, it's just speeding up or slowing down the star. I'll pass on.
All right. Okay. How do I forward? Okay. So the next, since we're doing this through simulations, we can look a bit more closely into what's causing the stellar activity signal. So we look here. This is for a shorter stellar rotation and a longer stellar rotation, and immediately obvious you can see that with the shorter stellar rotation, all the time scales are much shorter, as you would expect, because the stars rotate much quicker. But also the amplitudes here are higher. You can see that the change in flux is going from 4,000 to minus 4,000 parts per million, where here it's going from 3,000 to about negative 3,000. And same thing with the RV, amplitude goes up to about 40 meters per second, whereas here it goes up to only 25 meters per second. And then you can also look at the correlations between RV and other indicators you can pull out from your stellar spectra. And you can see here that for the faster rotators, you have slight correlations in all 3 of the indicators we can pull out. This is the bisector span, the full width half max, and the total flux. And there's weak correlations, whereas if you look at the slow rotator, there's only really the radial velocity is really only correlated with the full width half max. And there's a very strong correlator indicating that the full width half max is a good predictor for the stellar induced radial velocity signal. Another thing you can see if you look at the structure here is that since we do our simulations at finite time steps, the slower rotators, you have a lot more correlated structure, because since you're rotating a lot more slowly every time you rotate, your RV signal is going to be about the same as the previous time steps RV signal. So even though there's not very much correlation here, you can kind of tell that for the slower RV signals, you can use your previous RV signal and as a base, it's better for Gaussian processing things, because you can use your previous measurement as a much better predictor of what the next measurement is for your stellar activity jitter.
Okay, so now that we had looked at the effect of the rotation period on the activity RVs itself, we wanted to look at how well the injected planet was recovered, and we wanted to look at both whether that 23-day 5 meter per second planet was detectable and if it's the parameters that we derived were accurate. So here is the planet's period as derived from the MCMC fit to the data as a function of the stellar rotation period. You can see, so 23 is the true period, and you can see that it's accurately recovered for all stellar rotation periods, although when the planet period is close to the stellar rotation period, there's larger error bars on the planet period parameter estimate. And when you're further from the planet's period, then you have smaller error bars. Over here is a plot of the recovered semi-amplitude, and it's pretty consistent except for the one that's closest to when the stellar rotation period is closest to the planet period. And we think probably some of the planet's amplitude is absorbing some of the stellar activity signal, causing it to be kind of biased above the true value. Oops. So the previous slides looked at what parameters were covered for the planet, but this slide is looking at whether the planet was actually detectable. So basically, you run the MCMC on 80% of your data, use the prediction from those fits to predict the remaining 20%, and look at the comparison between running only the GP and running the GP plus planet. So you can see when the stellar rotation period is a harmonic of the true planet period, there's a smaller separation than when the planet rotation period is further separated from the planet's period. When you use this evidence threshold, actually 3 of our runs were not considered detectable. The ones that were furthest from the true planet period were considered detectable.
Okay, so just to summarize all the things that were discussed previously, we saw that stellar activity increases with rotation speed. The faster the star rotates, the more the spots are able to produce noise on all scales. Recovery of the planet signal is better when the planet's orbit period is far apart from the star's rotation period in both directions. We saw that, and the Bayesian evidence is also best in that case when the proportionate you'd like the ratio between the planet's orbital period and the star's orbital period to be as large or as small, not the star's orbital period, the star's rotation period, to be that ratio to be as small or as large as possible, and that gives you the best Bayesian evidence. And then we saw the effect of aliasing when we had the orbital period to be exactly half of we had the planet's orbital period to be exactly half of the star's. We had the star's rotation period to be exactly half of the planet's orbit period. Then we had exact aliasing effect, and that attenuated the RV signal, and the Bayesian evidence said that we didn't really detect it. Future, we could investigate this more fully by using a finer grid of stellar rotation periods to more fully sample the sensitivity of the Bayesian evidence to the stellar rotation, the Bayesian evidence, and also the recovery to the recovery of the planet's parameters to the stellar rotation period, and look for other points where the evidence might be low due to aliasing issues. And then the final part of the assignment would be to detect an Earth-like planet in the habitable zone of a Sun-like star. One thing we didn't really probe too much is we kept constant the star spot parameters, that is their lifetime distribution and so on, and we didn't really probe the effects of those. So
yeah, running out of time.
So hi everyone. So we have studied the effect of spots on the detectability of planets. So thanks to Xavier, we all know that there are many different sources of perturbation on RV due to stellar physics, and spots is actually the worst one, that's the one preventing us the most of detecting planets. So that's the one we have studied. So there are 2 effects of sunspots, the flux effect and the convection effect. The flux effect is due to the fact that the spot has a lower temperature and therefore fainter. So because the star rotates, there is a blue shifted side and a red shifted side on the sun. So if the spot happens to be on the blue shifted side of your star, then your star is going to appear red shifted, and it's obviously the inverse when it's on the other side. The convection effect is due to the fact that the convection is inhibited in the spots and around it. So, and the convection has a overall, creates a blue shift everywhere on your star. So if you have a spot somewhere, it makes your star appear redder, create a redshift. Sorry. Yeah. And so yeah, we have studied the effect of the temperature of the spot on planet detectability.
Okay, so as we all know that usually the spots would induce an RV signal, and the question that we wanted to answer is how does the planet detectability changes with the spot temperature? So what we did is two things. First, keeping all the parameters fixed, we changed only the temperature of the spot and checked the RV signal of the spot. And the second thing is that we injected the planetary signal, and again we checked whether the planetary can be detectable by changing the temperature of the spot.
All right, so first we're going to look at how just a spot by itself with no planet affects the measured RV signal that we detect. So first we take a spot and put it on the star, and then we adjust the temperature difference of that spot between it and the photosphere. So, and we use this SOAP 2.0 model that Xavier gave us. So what we're looking at here, let's take a look at this blue line first. This is just one spot on the star. What we see, if the temperature difference between the spot and the photosphere is 0, it's like there's really not a spot at all. So what we're getting is this just overall convective blue shift that we saw before. But as the temperature increases, the spots become more dominant, so the temperature difference is causing that the blue shift side to the red shift side. It's creating a overall RV signature that gets larger as the temperature difference increases. And one thing to note, so when we take this RV measurement, what we're doing is we're taking the semi-amplitude, so we take the maximum RV signal, subtract the minimum, and divide by 2. So then what we do is we increase, we now add a plage to that. So we just have a single spot and a single plage, and that's shown in the red line. What we're seeing is that the overall convective blue shift is now a little larger. The plage is contributing a larger, it's weighting more because it's a brighter area on the star, and so this is initially a little higher, and it takes a little longer for the spots to dominate, just because the spots are not, because there's a plage now, the spots are not able to take over as quickly.
So we ended up making a modified solar model, and what that means is we tried to create a realistic model of the sun, except that we made a couple changes that were in our guidelines for our question. So we set the solar rotation period to 5 days instead of 25 days like in real life, and the goal here was to make the effect of spots more dominant. Spots generally cause a flux effect, and that's going to be stronger if the star is rotating faster. So this will allow us to see our temperature dependence more easily. Then we added realistic plages around the star. So we center them on the spots, and we make them 10 times larger than the spot, because that's supposed to be a realistic size ratio. And then using Xavier's code, these features evolve, and they cluster at realistic longitudes and latitudes. And then we injected a planet. And we chose to use the same period in all of our trials. We chose 13.3 days because it was not multiple of our 5-day rotation period, and we didn't want to have any aliasing. So just like the other groups, we used the Gaussian process model, where we fit our data using an MC-MC, and we leave out 20% of our data points, and we try to come up with a predictive model that uses a GP only, and a GP and a planet fit. And then we compare the log likelihoods here. So in this example, this was for a run where we had a spot that was 300 Kelvin cooler than the photosphere for a 5 meter per second planet. And what we're looking for is the factor by which the, sorry, man, I knew it would happen to me. The GP and planet is preferred compared to the GP only. And here is what we find when we test a variety of different spot temperatures. What we plot here are the bounds that we were able to determine just by trial and error in order to kind of surround a GP plus planet model that was preferred by a factor of about e to the 5, which is about 150. And so this bar goes from about 7 to 8, which means that somewhere in here is where that transition point is. So you can see that when the spot is about the same temperature as the photosphere, it looks like we're only able to detect large planet signatures. And as the spot gets cooler, we're able to detect smaller planets. And this was a very surprising result for us, because it seems like if a spot is cooler, then it should have a larger RV signature and should cause more interference with our ability to find planets. But that's not what we found in this simulation, and Alex is going to tell you some of our theories on why that is. No pressure.
Okay, thanks. Let's see if this works. Oh, there we go. Okay. Okay. All right. So the explanation we kind of chose was that we had, between this previous simulation that Jake showed and the ones that Alan showed, we had increased our plage area by a factor of 10. So we think that our realistic model, which still has a stellar rotation period of 5 days, so we're still trying to enhance the spot flux effect, is still in this little region here where the sensitivity is actually decreasing with increasing temperature contrast. So our hypothesis that we're going to get a stronger RV signal to cover up the planets in the case of a bigger spot temperature contrast was only really valid in the region or in the situation where the spot flux effect is dominant. But I think in our realistic simulations, and here I'll go to the next one, our realistic simulations, we have so much plage area covered that the convective blue shift effect is dominant, and that's just covering up any signal we could hope to see from the spots in terms of the RV signals. So so that is our prediction that in any realistic model, well, at least if you accept that this factor of 10 area difference between plages and spots is realistic, which you can kind of see in this photo that I very selectively chose from the internet. If you believe that, then you're probably not going to see spots in most star activity signals. So, all right, thank you. Do you remember?
Yeah, so the Gaussian process, it takes for a time scale the rotation period of the star, which we assume that we know, and so it goes in as 5 days. And so it looks for correlations over 5-day time scales, and that's how it tries to model the activity. So it looks for correlations in the covariance matrix between a time at one point at one time and a point that's 5 days away from that. Yeah, we assume that we know the rotation period of the star, so that's included in our model.
Hi, I'm Carrie.
I'm John. And I'm guessing you can read the next name, so I'm Adam.
And I'm David. And several of us are ground-based astronomers, and our question was, what happens to the Bayesian evidence for detecting a planet as you vary the number of observations? And this was a point that we heard a lot about earlier in the week from Eric Feigelson, that he would like regularly spaced observations for decades if you could have it. Unfortunately, from ground-based astronomers, you don't have that luxury, and so we tried to simulate that, and we as a group happen to be interested in M-dwarfs, so we tweaked our parameters to try to fit to an M-dwarf. So we picked a temperature of a star that's 3,000 degrees, log G 4.5. Rotation period is a little bit longer than the sun at 33 days. Our star is a little bit shorter. We changed our limb darkening parameters to fit this type of M-dwarf. And so we used the SOAP 2.0 from Javi's script to do that. We said that the spots were not quite the same temperature differential that we have on the sun. So they would be 2,800, so a difference of 200. And we increased the amount of spots that you would have had fractionally by about 20% than what you might see on the sun. And then the durations were also increased. So 50% of the spot groups would have lasted for a couple hours through a little bit more than 2 days. 40% would have lasted for days through a couple of weeks, and 10% would have lasted for maybe as long as a couple of months. And here's kind of what that same animation looks like for our M dwarf.
Pretty. So we were a little ambitious in the beginning, and we wanted to simulate a multi-year survey. So we originally set out to generate a lot more data using the SOAP tool than we used originally. So we had the same cadence every 6 hours, but 4 years. And we injected a planet signal K of 3, period of 13 days, similar to Gliese 5A1b. So there's a nice picture. So the initial data set was pretty large, and we wanted to simulate this multi-year ground-based survey, so we applied several cuts to try to do that. First, maybe the most obvious is that you can only observe at night, so we had to get rid of every 2 of these observations, which were originally generated 6 hours apart. Second cut was to simulate seasons, so we assumed 8 months of observability per year. Third cut was for weather. This is maybe a little optimistic. And then the fourth was we injected once per season at a uniformly random moment in that season a major instrument problem with a duration drawn from a normal distribution with a mean of 15 days and 7 standard deviation. However, GPs are expensive. So we then realized that this was a bit too ambitious, and we decided to reduce the design a little bit from looking at multi-season comparisons to within a given season, simply how many months of data do we get. And so then within a given 8-month season, we just divided it up into months, and you can see these are what the data collection moments look like. So that's the first month in the top, all the way down to the last month, and you'll see that nasty instrument glitch there in the middle.
So we've all seen this before, so we're group 6, so we don't need to go over it in too much detail, but essentially we make a cut initially for a testing and a training data set essentially, and what we then do is we come up with 2 different models. One model just has a Gaussian process, not assuming any planet, and the second model we assume that we're modeling a planet. We inject a planet signature, and then we model it, and then we later compare to see which model better predicts our data. So I'll step through 1 month at a time for our 8-month observing season. And so shown here in the yellow is the likelihood for just the stellar variability model fitting, and in the pinky purple color is the stellar activity plus the radial velocity signature from a planet. So for our first month, with 1 month you can't really tell. The models predict the data about as well as each other. Still no planet with month 2. Month 3, still not really looking like a planet. But once we get to month 4, we can maybe say that we might have detected a planet. And at 5 months of data, we can say that we have a planet. And from here on, it's a question of possible diminishing returns, because telescope time is expensive, and we don't want to spend time observing something that we know is for sure there. So, moving on.
Right, so at this point, our models aren't getting any better without changing our priors on our analyses. So, what we did moving forward was look at what if we varied the period of our planet and how much observing time would it take to, say, find a longer period planet with the same K value. And what we find is that we're showing here a distribution of how our periods change over the number of observable months that we have with our telescope. And planets that we can definitively find or statistically find are in white, and this decreases, or this goes to the blue color as you lose that coverage. And for the first couple of trial periods, we get pretty good evidence that we may have planets over about a year's worth of observing time. But as we go to longer periods, it's going to require more time on the ground. So our conclusions are that more data means better results, but to a point, right? So like we saw here, we got really good results at 6 months, but it didn't get any better. So yeah, thank you.
That's a good thing to pay attention to. However, I think that's just noise in this case. So with 2 months of data, it's still a bit marginal, I guess. It's hand-wavy, just saying that 100 is a good cut. But I think when you're at that regime, it's pretty much the same. So if we had a different realization of the noise, we might see it the opposite. But the overall trends, I think, are pretty believable. So we were also a bit ambitious in the beginning, thinking about that as well, but we ran out of time. So we were also very interested to see, mostly because we'll be involved in doing stuff in the near future, that of course it might make sense to not do them consecutively. There's a lot of clever ways I'm sure you could optimize scheduling, but I think that would be a great exercise for the future. Well, in this case, when we compare so how we varied the amount of data that went into fitting was simply by adding additional months. So essentially what you're doing is sampling the signal of the planet better over a longer baseline. Right. So I think another thing to test would be to increase the number of observations per night. You know, there's a lot of different things we could vary. Yep.
I need to cut the video because we have
Oh.
behind schedule. So thanks again to all of you.
I'll leave you to wonder about that one.
Okay, so I'm Brian. I've got Jayesh, Bo, and Akshata with me here today. Joel couldn't be here today. And so we're the first group to talk about transits, and what we're going to look at is primarily the signal-to-noise ratio of a kind of typical hot Jupiter observation using James Webb. And we're going to talk about the effects of resolution and kind of binning spectrally on that signal-to-noise ratio and what is going to be required to accomplish our science goals. Okay, so again, we're going to take what's given, what's being delivered by the James Webb pipeline, the information that's provided, and we're going to look at what kind of signal-to-noise ratio we can achieve at any given wavelength, how binning the data changes those numbers, and then kind of evaluate what this trade-off is between resolution and signal-to-noise ratio. And then finally, we're going to take a look at what kind of precision is needed depending upon what type of planet we are observing and how that changes our requirements. So this is just a preview of what's going to be delivered by level 3 James Webb data. It's going to be, the level 3 is time series data delivered as 2048 by 2 tables. That 2048 is the spectral direction. The 2 is just the a wavelength for each one, and the intensity. And in this particular case, in our example data that we were given, there's 144 of these tables, and the 144 is the temporal direction. Each one of those 144 tables represents a 33-second integration time. And so we're going to calculate what the signal-to-noise ratio at each wavelength is based upon that given information and the information from the FITS header that the gain of the instrument is 1.5 electrons per dN. And just to kind of point out here these plots, so this is what any one given table plotted out would look like. This is your 2048 direction in wavelength across the x-axis and your intensity going in y. And so if you were to integrate each one of these, if you integrate each one of these tables and plot them in a time series, you would get a nice, beautiful, noiseless transit light curve, right? Yes, yes, we have beautiful noiseless data at this point for this exercise. Okay, so again, the assumptions here that we're working with is that we have photon noise limited observations, and the other thing that we're assuming is this observation is just a kind of a typical star where we might find a hot Jupiter planet. Just given what we see here, we can kind of get an idea of what the temperature of the star is based upon the peak of the spectrum there. So this is about a 3,000 degree Kelvin star. We can't say much about its luminosity without having kind of the flux conversion factor, which you would have given in a Webb sample, but we didn't really have it here. So this is kind of modeled across, from what I gather, this is modeled off of a star that's about 3,000 Kelvin and like a a K-band magnitude of around 9. So if we do just that, if we kind of integrated each wavelength, we assume that we're photon noise limited, so that our signal to noise ratio is just going to be a function of the number of electrons that are generated. We can figure out what the signal noise ratio is as a function of wavelength, and kind of down here at the bottom is kind of our, not really binning down at all. This is really kind of a native resolution of about 700 or 1,000 or so if we don't do any binning of those 2,048 points. And so without doing any binning whatsoever, you can see we have a signal to noise ratio of somewhere around 10 to the third. And of course, as we start to bin in the spectral direction, we can drive that up, but our resolution, of course, is going to go down. So the question becomes, what do we need to do in order to achieve our science mission? And I'm going to skip this one. I'll kind of come back to it later. This is just the inverse of the signal-to-noise ratio showing us what our sensitivity is. And okay, so we're going to want to talk about detecting spectral features. And again, I'm going to go through this quickly because I'm going to touch on it later. But this is just to show that the depth of the spectral features, the strength of the spectral features that we want to observe are a function of two things that we're going to consider. One is the radius of the planet, and the other is the scale height h, which of course h is directly proportional to the temperature. So when we talk about what we need as far as signal to noise ratio for a detection in a hot Jupiter versus an Earth-sized cool planet, obviously h and r are going to be very, very different. So that's going to lead to having very different requirements. So what we've done is we've used the model provided by Mike Line for this exercise to generate kind of just a typical hot Jupiter type of a spectrum over the bandwidth that we're considering here, and we're going to pick out this big broad water feature right there at around 1.4 microns, and see what we would need to do in order to ensure that we were going to detect that. And so what we can see here is if you look at the amplitude of this signal, we're at roughly 300 ppm. We're going to use nice round numbers here just to keep everything nice and easy. So if we said this is about a 300 ppm signal, if we want a 3 sigma detection, we're going to need 100 ppm sensitivity. So what we want to consider then is what that means in terms of resolution, in terms of getting the SNR we need as far as resolution goes. So if we go back to this plot that we kind of threw up there a little bit earlier, we can see that if we need, let's see, go backwards again. So we need 100 ppm precision. So this is why we've kind of inverted this plot to make it nice and easy. So we can go right here without having to do any conversions. Say, okay, 100 ppm precision, and this R of 100 or this R of 10 pretty much get you where you need to be, plus or minus a little bit, right? But now let's vary the system parameters. Let's take that temperature and drop the temperature down from 1500 degrees Kelvin to 500 Kelvin or something. Let's take the radius of the planet and reduce it by a factor of 10, and then let's see what the amplitude of the signal is that we're still trying to detect. So if we're trying to find water on, say, some super Earth type planet, now our signal is on the order of maybe 60 or 70 ppm. So the sensitivity required for detection is going to be somewhere around 20 ppm. Again, going back to our sensitivity plots here, so you can see what we need to achieve somewhere way down here, which is well below any of the curves that we've chosen to show. Well, why don't we just keep going down in resolution and bin and bin and bin? Well, at some point, right around R of 10, you get to the point where you won't have the resolution required to detect even a feature as wide as the water features that we're looking at. So there's a limit to how much you can spectrally bin and still detect your features. And so at that R of 10, that's about as low as we would want to go spectrally. So how do we get there? How do we build up the signal to noise in order to make a detection of water on a super Earth? Well, we need to increase this. We need to increase this by about a factor of 3. So we need 9 more observations. We can get it through performing nine transits rather than just one single transit. So in conclusion, just to kind of wrap this up, kind of as we would expect, lower spectral resolution gives us a higher signal to noise ratio, but again, we can only lower that spectral resolution to the extent that we can still have enough sensitivity to detect for the width of the features that we're trying to detect. And then, of course, as the temperature increases and the radius increases, that scale height goes up. The size of the annulus in which the light from the star is passing through is increased, and so we're going to get more absorption and thus bigger features that are easier to detect. With that, we'll open it up to questions. Yeah, absolutely. So we kind of took the easy way out, right? Looking at a big, broad water feature. As you start to look at different features, these methane features, for example, that are much more narrow, the resolution required is going to be higher, and so you won't be able to drive the SNR up as much by binning. You may need additional transits or a brighter target or something like that to get the signal to noise ratio that you need.
Thank you. Group 1.
Don't pass. Unfortunately, we're a very big group, so we may have some logistical issues in terms of all of us speaking. So you can see our names here. It probably saves time rather than going through everybody. So we are group 2 in the transit exercise. As you can see, we're looking at the effect of wavelengths and spectral type on light curves. Just very quickly, we've put all of the code that we've been working on throughout the week on GitHub. So if you want to look into it in more detail or check our results, then you can here. So our project goal was to look at how the transit shape changes with respect to different wavelengths. So similarly to the first group, for those who were working on the transit exercises, the first part will look very familiar. So we were looking at the hypothetical JWST data and looking to build a white light curve from that. After that, we were estimating the depth of the transit, again looking at estimating roughly the planet radius, and then investigating different types of star and planet combinations that would fit the data that we saw. And then after that, we looked into a bit more detail about how the shape of the transit and the depth would change as a function of wavelength. So I will pass on to Jessica.
Thanks very much. Do we have a thing?
Oh, yeah, we do.
Oh, yeah, thanks. So Brian actually just covered everything I wanted to say on this slide. So we were using simulated observations of a single planetary transit from the nearest instrument from JWST in single object slitless spectroscopy mode.
the only new thing I have to add here is we have a lovely image of the actual exposures here. Oh no, that's too far. Oh dear. How do you do this? Oh, there we go, yeah. And you can see the actual spectrum here. So you turn this into a 1D spectrum, and to get your white light curve, you simply sum underneath all these wavelengths, put it against time, and as you can see here, we have the transit, and there's no need for Bayesian statistics to tell us that there is a planet in this data here. The next step is simply, to estimate by eye the transit depth. You can see here that it's about 1.5%. So take the square root of that to get the ratio of the planetary radius to the stellar radius. Gives you a planetary radius of about 12% of the stellar radius. Next, to get the absolute planetary radius, you need a estimate of your stellar radius. So as Brian explained, you can do this by analysing the spectrum of your star. But we have a spoiler for you. This data was generated for the case of HD2I9, which has a stellar radius of about 1.14 solar radii. So 12% of this gives you a planetary radius of about 1.35 Jupiter radii. So this is a large planet. This is the size of an inflated gas giant planet. And for different for different stellar types and different combinations of stellar types and planetary radii, you can actually end up with the same transit depth. So what we're showing here is lines of constant transit depth for a broad range of planetary radii and stellar types. So you can see HD2I9 here. So a transit depth of 1.5% could come from inflated gas giant around an early G-type star, or equivalently from a roughly Earth-sized planet around a late M dwarf. And this plot here just shows lines of constant planetary radii for various transit depths. With that, I'll hand over to Juan Carlos. Or Ben, actually. Change agenda, sorry.
So just briefly to follow on from the previous plot, we were asked to consider why small M dwarf stars are advantageous as host stars. So basically, for a given type of planet, the smaller the host star, the more light is going to be blocked out, and so you'll get a bigger signal. And similarly, going to smaller stars allows you to detect smaller planets. There's the additional benefit that they're by far the most common type of stars in our galaxy, so there's plenty of choice for targets. It's perhaps worth noting that while they're good for detecting planets, they're maybe not so good for finding life on these planets because the habitable zones are so close in to M dwarfs. Planets that could harbour life would be likely to be tidally locked and have large temperature gradients. So.
And in the next step, we then considered how the light curve will change at different wavelengths. So what we did was spinning the spectrum that you saw before into several wavelength bands. And instead of integrating over the whole spectrum, we just integrated within one of these bands and plotted, instead of the white light curve, this series of, I think here we have 10 different wavelength bands. And you see in the end that the observation wavelength affects our transit depth. So at short wavelengths we have deeper transits, and we see a wider planet, meaning we see more of the atmosphere, basically. And to not bore everybody from the transit group, because that's what everybody did in the hands-on session, but also not to leave out the RV people, we redid the exercise that we had in the transit session with a different spectra. And Jason was so nice to generate JWST simulated spectra for GJ1214, which we can see in the upper left there. And we went through the steps again. So we went over the entire wavelength band, made a white light curve, then we fitted the white light curve because we have a lot of data there. We do an MCMC, find out the parameters, and use those as priors for then our fits of the various different wavelength bands. And so we see here again, we have this like dispersion between different wavelengths, how they affect the depth of the planet that we see.
how much of the atmosphere we see. And as good scientists, we of course give our posterior distributions. And in the end, there's something that's in my slides, but it didn't make it to the submission time, unfortunately. We went from this and plotted basically our depth that we see here over the different wavelength bands, meaning we extracted our spectra. And we can see Gliese 1214 is quite cloudy, as Laura Kreitberg et al. Have already published in 2014. Thank you. Next one.
I missed that one. Then we try to characterize the planet in the G star, so the first one that we showed. So you see how the transit depth decreases as in wavelength, and you have, if you bin too much, I mean that's what we've been told, don't overbin your data because you might lose some signal. As you see here, this is 10 bins, this is 100, and you see you will lose. If you have the signal to noise, just try to avoid overbinning. And the word about limb darkening. So this, this has been told, but if you see the star, you will see the red to the edges, and there is an effect for people who actually works on limb darkening. This is a linear fit, so it's probably not the good idea to use, but it's just for it's easy to see. So the bluer you are, the more darkening. So yeah, you can see that the slope is much more pronounced in the limb darkening than in the transit. Just see at the scale in the y-axis. So you might think, oh, maybe this is very correlated, these two parameters, but as we've been shown here, they are not. They have some correlation, but it's not as bad. And the thing is, what basically limb darkening is doing is just reshaping the ingress and exit of the transit, not as much as the depth of the transit. So I leave you with the conclusions.
Yes, I can just read to you what's on the slide or just very quickly summarize. So we were looking at the effect of looking at different wavelengths and how that changes the transit shape. I think the best graph that we've pulled together so far that shows it quite nicely is this one here. So you can see as the wavelength gets longer, the transit gets flatter. Going back to that summary slide. We made quite a few assumptions. So we were looking, again, as we said before, we took the stellar radius as given when we were trying to figure out what the size of the actual planet would be. Again, if you consider the star being of a different size, so slightly smaller or larger, then we may have a different approximation there. I guess the end question is, do we see an effect of how the transit changes with wavelength? And the answer is yes, we do. So, any questions?
All right, so our presentation is designed to wake you up after a few transit talks, and hopefully it will do its job appropriately. We're going to be presenting to you on limb darkening, which you just heard a little bit about, and I'm going to try to motivate that it's interesting enough to be worthy of a whole other presentation. And so let's review what limb darkening is, because some people who don't think about stars very often might not actually have really played with limb darkening that much in real life. If you look at real stars change brightness from the center of the stellar disk to the limb. And this is a real star. This is the sun. And as the sun rotates, you can see star spots rotating into and out of view. If you were to try to approximate the change in flux from the center of the stellar disk to the limb, how would you do that? Would you approximate it as a linear trend? Would you approximate it as a quadratic trend? Would you use something even more complicated? I don't know what you personally would use, but we decided to try a bunch of different options because in real life, physics tells us that none of these are actually valid approximations to the limb darkening law that behaves on real stars. But as people fitting noisy transit light curves and noisy bins of transmission spectra, we know that we have limited information to constrain the stellar properties. And so we usually want to summarize the limb darkening as 1, 2, or 3 parameters, but not 5 or 10. And so we want to use a simple function, but not the wrong function, or a function that would bias our transit depth. Because spots like these, and this will come up again later. Spots like these can bias what your transit depth would appear to be, and also your limb darkening, and since all those parameters are tied together, you have to be careful how you treat these stellar parameters. And so to motivate where this becomes important in spectroscopy, in transmission spectroscopy, let's review what the reason for limb darkening is. The reason is that when you look at the stellar atmosphere, when you look towards the limb of the star, you're seeing higher layers in the stellar atmosphere. Higher layers in the stellar atmosphere are cooler than the deeper layers, which you see at the center of the stellar disk. And when you look at the higher layers, which are cooler than the center of the disk, where it is hotter, the temperature difference is shown most at the bluest wavelengths. When you're looking in the blue, the change in flux is great for a small change in temperature compared to the red. And so what you see when you look at transit light curves as a function of wavelength, as you saw in the last talk and as you'll see again in this one, here's HD 209's actual spectrum. It's the same planet from last time. But this is an observed spectrum from Heather Knudsen, who presented this earlier this week. You can see that the limb darkening is strongest in the bluest wavelengths, or I'll go the other way around. In the longest wavelengths, you get corners at the bottom of the transit because the limb darkening trend isn't that strong. It's pretty flat bottomed in the transit. And at bluer wavelengths, you see more rounded light curves. And so if you were making the wrong assumption about where your limb darkening parameters or their parameterization are, then you would infer the wrong transit depth, which as a function of wavelength gives you the spectrum of the planet, so you don't want to mess that up.
Okay. All right, so one of the main things we want to look at with limb darkening is the effects of parameterization on the transmission spectrum. And as we go forward. So our main goal here was to test the different models. Throughout this conference, it's kind of been beaten into us that we have all these different models and they should converge on the same results. And we wanted to make sure that that's actually true here. So we were hoping to test all these different models and find a 1 sigma agreement on all of the points. And so we started off by using our simulated data set from the Jimmy Webb Space Telescope there. And we see that we find the similar results to the Heather Knudsen paper, that the redder wavelengths do have a more box-like shape and the bluer wavelengths do present a more narrow band. And thus that is accurate. And so our next step was to test the different models. So there's several different models. The ones that we really looked at in this paper, or I shouldn't say paper, in this presentation was the linear, the quadratic, exponential, and the nonlinear. We skipped those other three because we just didn't like them. No real reason. But we tested these four, and we were hoping to find that they would all give us the same answer at the end of the day, which I will lead on to Luke.
That was quite a setup, so I'm not going to actually immediately show you the answer. I will first show you what we're actually fitting for these different light curves. So you saw the light curves, and that was basically our raw data. And for each of these light curves, we are fitting for the linear limb darkening parameter in just this one case. Although for the different limb darkening models, we are fitting for the different limb darkening parameters, and for the mid-transit time, and then also for the radius. So the priors that we're using in this routine are uniform on all these parameters, and our likelihood is Gaussian. So here are some more of our posteriors for basically different wavelength bins. And going right along, here is that transition that John had set up for me. So you've already seen this plot in the previous talk, but basically the result is that for linear limb darkening coefficients, you see, well, basically more limb darkening at shorter wavelengths, or so closer towards the blue, which means that we have a larger limb to center intensity ratio at bluer wavelengths. So when we actually ask what does this mean about our derived transmission spectra, so here I'm showing you the RP over R star, or the square root of the depth from the previous slide as a function of wavelength, and all these different squiggly dots are the different limb darkening parameters. So we're showing the quadratic, the nonlinear, the linear, and the exponential fits, or the not really fits, derived parameters. And all these values are roughly consistent to about 1 sigma. So the takeaway for this is that if you want to derive order of magnitude constraints, and you're not really interested in doing anything particularly precise, well, any limb darkening parameter here is fine. The linear is cheapest, so you might as well do the cheapest thing computationally. That said, if you want to do anything precise, which often you do because it matters a lot for constraining the actual physics of your planets, then you should probably be more careful. Tony has a lot more.
Not a lot more. I'm just here to wrap things up. So, just as a little disclaimer, I guess I'm the one to reveal the disclaimer. We need to make sure that the MCMC or the chains that we have run have actually converged. That's always a little disclaimer. If they obviously haven't converged, then we need to look a little bit more into this. So just keep that in mind. So for future work, we could probably one of the biggest things is looking at stellar activity. That's been one of the large discussions at this workshop. And so things like sunspots and flares are obviously going to be affecting our data. It's going to depend on which wavelength we're looking at. Solar prominences, depending on which wavelength obviously we're going to look at, it'll depend on where on the star it's also occurring. We're going to have different features showing up. So those are all things that would be good to look forward to in the future. And of course, we need to sample efficiently. This will help with computational things. So I'll refer that off to David Kipping. So thank you. Nope. Oh, that is references. So we are done. Thank you.
We did not. I mean, so
I was going to put some more detail into that, but
yeah,
no,
if
you're
you'd
right.
like to add some detail.
Well, it's just we injected noise into the transit light curve so that we could imagine that we had some uncertainty about what the limb darkening properties should be, and so to the amount of noise that we put in, you couldn't see a difference, so we didn't look at the residuals because there wouldn't have been anything to see. There was too much noise in our data. But no, we didn't look, so that's the right way to say that, yeah.
All right, home stretch. Hello, everybody. I am Sean. I'm part of this wonderful group of wonderful astronomers. We were group number 4 for the transits, and our project was to explore the how adding additional planetary parameters to the MCMC fitting affected the errors we would get from those fits. In particular, we started out with 3 parameters: the mid-time transit, the limb darkening law U, and the radius ratio. We're also exploring that. We had to add the semi-major axis A and the inclination I into the set of fitted parameters. And looking at the changes in the uncertainties, as I said, and then also discuss how we could limit the parameter correlation and incorporate other information to adjust that. So some of our hypotheses before we got started, I wasn't too familiar with statistics. So I thought increasing the number of parameters would reduce the errors, thinking you're coming at the answer from more angles. You could probably find it more accurately. Others who are more familiar with statistics, they dissented. They said that adding more parameters would increase the errors because statistics is, quote, a dark art and sorcery. That's the master statistician up there. We also thought perhaps increasing the number of chains in the MCMC would also reduce the error. So what we did as a group, we took the Scooby-Doo approach. We split up, gang, and pairs broke off and did 3 parameters, 4 parameters with the 4th being inclination, 4 parameters with the 4th being A, the semi-major axis, and all 5 altogether. And then at some point along the way, our mystery machine kind of broke down, and everyone got so into the MCMC code that we did different parameters for that code. So there's a lot of different ways we changed the number of walkers and the burn-in values, but you're going to see all the gooey, gory details as we go through our presentation, so don't worry. We assumed uniform distribution for our priors, and we kept a constant in the MCMC model at 5,000 iterations. So here is the 3 parameter results.
I don't have too much things to say because the last talk was so clear. Yeah. And well, just to say that we launched the MCMC routine with the 3 parameters: the radius of the planet, the linear dark linking parameter, we didn't have cuts, and mid-transit time. And just to say some correlation with the limb darkening and the radius of the planet, and just pick up the radius of the planet in units of the radius of the stellar mass to make some conclusion at the end of the talk. Just to say, we launched 2 different same workers chains, 100 and 300, and the results are similar. And the next step is adding more parameters. That's another slide.
Okay, so I'm Eloise, and Kelsey was working. We were working together to do this one. So we added inclination as our 4th parameter. So here we've got one plot with the burn-in just being 50 and the other one being 1,000 with 5,000 iterations. Basically what you can see here is that there's not much correlation between any of the parameters, so in the one on the left, except for between the radius of the planet and the limb darkening. So the next group will tell you what they added.
Thank you. For those of you who don't know me, my name is Bernie Uhas, and for those of you who do, I apologize in advance. I was working with Tiffany. We both represent Kutztown University. Similar story going on here. We have these basically same initial parameters, except we were now varying the semi-major access. Burn-in of 50, burn-in of 1,000. Obviously, I'd like to focus your attention on this one because the results actually look pretty decent. We observe a correlation between the linear limb darkening radius of the planet and the semi-major axis and the radius of the planet and the linear limb darkening. Nothing too terribly surprising, except the results do look very nice. So yeah, pass it on to the next one.
All right. So further regarding the this is the right one. So further regarding the semi-major axis, we decided to add a few more plots to as an emphasis what we already discovered in the plots. We have here on the top row a development of the N walkers value. We start with 100, go to 500, and eventually 1,000, and we see actually a clear trend in the graphics. There is a saturation over the value with increasing number. So we can say that initially increasing the value helps you to get contrast into your graphics, but eventually you don't want to add too much since you want to get a proper contrast. Furthermore, we also did a small change in the burn-in value. And this is a quantity that refers to how many of the initial steps you take out of your statistics you just neglect because of their randomness, more or less. In the upper plot, we have included more data points, and we see that we add more material that is random compared to the bottom one, where we throw out thousands of the first dots, and we end up having a much nicer, smoother circular figures. So you have to figure out a sweet spot in your N walkers and burn-in values.
So for the last analysis with Ximena and myself, Clement, we do MCMC analysis with the 5 parameters. So where is the, okay, the radius reduce ratio with the star and the planets, the limb darkening, the T0, the semi-major axis, and the inclinations, with 3 different values of the burn-in, because the problem is with 5 parameters, so we have a lot of way. The parameters move a lot during the MCMC. We have the travel from the initial plot and the initial values to the base values found. So it's more clear in this graph. Like the previous analysis, we found correlation between the reduce ratio and the limb darkening and the semi-major axis, so it makes sense. For the inclinations, the graphics looks like strange, but it's not strange. Just we find two values, two results, who are the opposites rather than the reference of the 90 degrees. So it's just a numerical biases. So I think that's all.
So all together now, looking at the different, how the error changed as we increased the parameters. You sort of could pick that up as we went down in the slides, and the variation in the MC was as we went across in the slides. As we added parameters, it increased the error. Well, there also was no discernible trend that we could really see in how adding additional planetary parameters affected what the actual median value of the radius ratio was from our posteriors. For the first bits, as we add as we add inclination, it goes up a little, or it goes down a little bit, and then by the time we add, it goes down again, and then we add to the 5th parameter, it goes back up. So we're not exactly sure what's going on there. Some parting thoughts. So increasing the number of walkers for the MCMC chain, as we learned, seemed only to increase the error in the fits. It saturated it, like Nestor said. Increasing the number of parameters also increased the error, as we just said. But what we discovered is that increasing the burden number had the most significant impact on decorrelating our posteriors and really cleaning that data up. So for some of us, our initial hypotheses were ultimately wrong, meaning that the evil sorcery that is statistics has prevailed over us. Thank you.
We're group 5 for transits, and we were asked a simple question of how do you like it? But that's not a very scientific question. So the scientific question was to investigate how the spectral shape changes as a function of temperature and assume composition, specifically the composition of the atmosphere. So going into more what that means is we're looking at 3 specific things. We're looking at how temperature changes the spectral features, how the abundance of water changes the spectral features, and then also just many different molecules and their abundances and how that affects the spectral features. Now, something to take of note is what we used the planet that Mike Line was so courteous to give to us, which is supposed to be a hot Jupiter, except for when we obviously are varying the temperature. It's going to go from cold to hot. But we did not look at the star at all. We just assumed the star was some constant star that we were unsure of what it was exactly, but we were just specifically looking at the planet and its own atmospheres. So going around the group, just so that way we all get introduced, we have Ben, and then we have Clara, myself, Jesse, and then Lorenzo, Ping Hui, and then Jessica and Kyle. So I'm going to pass it off to Jessica for our first section.
All right, so I just investigated how temperature changes the spectral features. So this was using Mike Line's code, and he put in a certain amount of abundance of methane, water, carbon monoxide, carbon dioxide, and a bunch of other things in there. But the goal was to hold it constant and then see what would happen if we have a cold Jupiter versus a hot Jupiter. And so if we look at this, so up here, I know it says relative eclipse depth. It's actually relative transit depth. And then this is our wavelength here. And here's our temperature. And if we heat the planet up slowly, you can see that the spectral features become much bigger, much more pronounced. And this is actually really important for a couple of reasons. So if we go over here to compare it, okay, so first backing up, why does this happen? This happens because the absorption percent during transit is dependent on our scale height. And scale height, if we hold the molecular abundance constant, scale height's dependent on temperature. And for those of you who maybe aren't clear what scale height was, I actually had to Google it at the start of this workshop, it tells you how your density is distributed in the atmosphere. So 1 scale height means that the density has decreased by a factor of 1/e. So if you have a really cold planet, like this, you have a very small scale height. That means that most of the density is close to the surface. So you're not going to get as much, you don't have as much atmosphere to look at. And so your difference between one planetary radius, one transit depth compared to another is very small. Whereas if you have a really large scale height, you have a lot of atmosphere to work with. And so your difference between your two heights is going to be more pronounced, and hence your spectral features are going to be bigger. Two things to note about this. The first one is this is why we really need to know the temperature of the planet we're looking at, because you could say, oh, well, this feature is more pronounced, so therefore we have more of whatever this feature is. Or it could just mean that the planet's hotter. The other thing to note is that this is around the temperature of an Earth. Well, it's not, we're looking at a cold Jupiter-sized planet, but it means that colder planets' atmospheres, the spectral features are harder to detect. So when JWST goes up, we probably want to start looking at hotter planets and then slowly start looking at the colder ones. It's just going to be harder, so we need to make our detection methods better. Okay.
Thanks. So, okay, next step. We keep the temperature fixed because now we know everything about how it affects the spectrum, and we specifically focus on water. Why water? Because we know that planets have water. HST has given us several beautiful spectra of water. We already saw them during this workshop. And water is important for formation of planets and many other reasons. So let's look how the spectrum changes if we increase the amount of water present in the atmosphere. We're using a simple model containing just helium and hydrogen and water. Helium and hydrogen have a spectral signature. You can see it here. Here you have Rayleigh scattering, and this is called CIA, but whatever it is, this is not what we're looking for. We're looking for water. Let's increase slowly the abundance. So if we're looking for water, we want wetter atmospheres, spectra like it wet, but up to a certain point. You can see that when the abundance here, the abundance is only water, no more helium and hydrogen, just water, but the spectral features have decreased. This is, again, because of the scale height. As Jessica told us, if the scale height is lower, the signal in transmission will be lower. And you can see here, this mu stands for molecular weight. Water is a heavy molecule. If you put too much, then the spectral features will become lower again. And we also wanted to focus on which wavelength ranges are more sensitive to water. So if we change a little bit around the solar abundance of water, 10 to the minus 3, where should we focus to find the best change, the biggest changes? That's where we want to really look with our telescopes to find the differences. And you can see here, the thicker regions are where we actually find the biggest differences. Why is that? That's because those are exactly the regions where hydrogen and helium have the most absorption. So if we decrease the amount of water, we're going to see the bump due to hydrogen and helium, and the Rayleigh as well. So basically, the conclusion is that where the difference is maximum, there we should look. And as a little exercise, we tried to verify this hypothesis by adding CO. So you can see the red line changes, and it has some other features. So where would you expect the water spectra to be more different now? Anybody has an idea? Too bad. That's the point. That's the spectral feature of CO. It's pretty peculiar. You see that there's a bump, and indeed, if we had water, that's where we had the best difference in the spectra. So I'm gonna pass Clara
the bowl. She has more to say us about this.
Okay, so finally, it gets really messy as soon as you start adding more molecules. Here are 6 molecules, and you, of course, I'm sure are wondering, how did we get these amazing plots? So worry not. If you go to Examol, you can choose your molecule, and just a random molecule, phosphine, although it's great. You can choose your bin, your range, and your temperature, and just plot anything. So if you do it for every molecule, you can see that in this case, although water is kind of the famous one, if everything had the same abundance, then you can get quite a lot of spectral features that compete with water in lots of points. And then, of course, if you have lots of molecules together, you have a cumulative effect in the final spectra. So it's not like the one who wins is the one you see. So we tried to compare this to the model, Mike Klein's model. So these are imaginary and totally, mostly in physical atmospheres that are either water-rich, methane, carbon monoxide, ammonia, or nitrogen-rich. And here you can see these features, and it's quite hard to put them next to each other, but the features, of course, match the fundamental cross-sections. This is not a coincidence. That's, just what the molecules look like. But if you then try to combine them all together and try to see which features kind of survive this battle of the molecules, the top graph is the atmosphere. If you made all of these 5 molecules in equal abundance, of course this wouldn't happen, but you can see the water features are still reasonably prominent, but it's quite important to note, so where water has a window, which is here, you end up getting this flat line because of the competing efforts of the ammonia and the methane cross-sections. And then what I would like you to be aware of, although there's lots of things you could say about these graphs, is here where you see a clear feature, so you think this is water. So that's this water. It has a lot more to do with the fact that the line lists for ammonia and methane and any other molecule in this region have never really been measured or calculated. But by looking at this graph, you can see that they do probably exist here. They just haven't been measured. So don't just believe that there's water. Check whether there should be some line list there or not. So I'll take you to...
Thank you. Just to quickly wrap up, we took a transit spectra and checked to see how various parameters cause it to change. You'll notice as the temperature increases, the spectral features become more prominent, and this is due to scale height. In a similar way, as you increase water abundance, water's features begin to, at first, become more prominent, but then due to a scale height decrease, become suppressed. And finally, most significant spectral features depend on the ratio of molecular abundances, so use good molecular data or your model will be wrong. Thank you.
Hello, everybody. And so we're your final group today, and I think we're going to be short and sweet with it. So we were asked to investigate the effect of clouds on spectral retrieval, and so during the hands-on session, we were able to play around with these different models and tweak the temperature and clouds and molecular abundances. And so to first order, I'm just going to tell you what happens when you add some clouds to your model. And so on the left, we have this clear spectrum, and then what you can immediately see with the when you start adding clouds is that you start to flatten out your spectrum, and it affects the shorter wavelengths at the very almost immediately. And so for our, we weren't asked to really fit anything. We were just asked to interpret stuff. So with that quick primer, you should be able to look at these posteriors and understand completely your planet, right? We're done. No, just kidding. So we were asked to make sense out of these 3 different posterior distributions for the 3 atmospheric retrievals, and the parameters that were fit in these particular models were temperature, planet radius, amount of clouds, and the molecular abundances. And so on the very left, we have just a clear atmosphere that was fit with all of these parameters. Then we also have a cloudy atmosphere, and then on the very right, we have this an actually cloudy planet atmosphere, but it was assumed clear. And so how did that affect the posterior distribution? And so the things that all of us thought really hard about and that they're going to explain to you in the next few slides is actually the physical scale of the atmosphere above the planet's surface, how these molecular abundances and the corresponding uncertainties changed with the different assumptions, and the importance of having an actual reasonable model selection that you fit to your data. So, who's next?
So one of the things that's been drilled into us over the course of this workshop is that clouds kind of suck, and we found that to definitely be true. So what this is a cut of the posterior distributions that were just shown in the last slide. What's shown is the temperature and radius being compared, and you can see there's a strong correlation that's kind of been talked about a little bit in the with the past groups. The thing I want to kind of focus on, though, is that with the clear atmosphere retrieved with a clear model and with the cloudy atmosphere retrieved with a cloudy model, you get pretty self-consistent temperature ranges around 1500 Kelvin. One thing to point out, which you probably can't read because I can barely read it, is that the uncertainties on the temperature for the cloudy model have increased by roughly an order of magnitude from 10 Kelvin to about 100 Kelvin. So part of that is the introduction of new parameters, and it kind of demonstrates that because of the clouds, you have less certainty about the specific number for your temperature. To contrast this is the cloudy atmosphere retrieved with a clear model, and you can maybe read that that temperature is roughly 400 Kelvin, but that the error bars are still order 10 Kelvin. So if you end up trying to fit an actual cloudy atmosphere with a clear model, you might be deceived into thinking your temperature is well restrained within a certain region, but could be something vastly different, because the two cloudy atmospheres were actually the exact same between the different model retrievals. So the takeaway is kind of that you can't ignore clouds, and we're then going to talk about why this correlation kind of exists between temperature and radius in a more intuitive sense.
Cool. So before I switch slides, I want to point out actually the radius also changed. These two parameters are degenerate. And we came up with a kind of schematic explanation of that degeneracy and why the cloudy spectra fit with a clear model got it so wrong. So if you imagine a cloudy planet, it has some radius and then a cloud deck and then a thin atmosphere above it. If you try and fit that same spectra without the clouds, to compensate for the deeper transit that the clouds provide, the radius gets bumped up, but the atmospheric features need to be recovered. So the same kind of thickness of the transparent atmosphere is recovered in the clear model fit to the cloudy data by shrinking down the thickness of the atmosphere. And as we talked about before, the main way you do that is by lowering the temperature.
Moving on to the abundances of various molecules retrieved, we can see that in the cloudy model, due to the gray absorption of the clouds, which will lead to an overall suppression of all the spectral features, the signal-to-noise ratio of the spectrum is hence lower, and the uncertainties on various abundance increased, especially HO2, which is the dominant species in this particular model. The other thing we noticed was that in the cloudy model, when the cloudy model was retrieved without taking the clouds into account, we saw a false detection of CO2 molecule. Here we are showing the posterior distribution of CO2 abundances in the clear model and the cloudy model retrieved as clear. You can see here the CO2 molecule is detected at high confidence falsely. The reason we think this case is twofold. Firstly, if we increase the CO2 abundances, it also increases the mean molecular weight of the atmosphere and thus decreases scale height. As a result, the entire spectrum will shift down to account for the cloud effect. The second reason we think is that increasing the CO2 abundance also helps to account for any remaining spectrum in the cloudy spectrum. These problems, sorry. All right. These problems are largely solved when the clouds are properly accounted for. The abundance of various molecules retrieved in the cloudy model are now consistent with the clear model. We argue that this success owes greatly to the fact that, to the fact that clouds have not completely suppressed the spectral features. As we will see in the next slide, the cloudy model is actually quite not very cloudy. It still preserves many of the spectral features, and we suspect in the most extreme case, when the cloud completely inundates the spectral features, such retrieval model will probably not tell us much more about the atmosphere. Moving on.
So we already heard that basically if you ignore clouds, it's really bad. So I'm just here to show you that if you do run your MCMC and you get your model to converge, there's all hope isn't lost if you just look at the best fit. So you can't really tell very well because they plotted in a green color. We were given these plots, so sorry. But in the shorter wavelengths, Raquel mentioned that when you add clouds, it just flattens in the shorter wavelengths much faster. So the red line is what it actually is, and if you can actually see it, it actually fits the model spectral features in the shorter wavelengths that aren't actually there because we're assuming that the atmosphere is clear. It's more obvious in the wavelengths at about 2 to 2.5 microns that the best fit model in green does not match the red on the bottom. So basically if you calculated a chi-squared of the fit, you would see it was bad, and then maybe you can add clouds to your model and test that.
Okay, so I'm just going to kind of sum up what we learned that we need to think about when we're actually doing these with real planets rather than planets that we've made up. So firstly, JWST spectra are actually going to do really well. I was really surprised how good the temperature determination was for the clear model that we fit accurately. So that's going to be really cool. But if you get your models wrong, you can draw completely wrong conclusions and you might think that they're quite good. So we need to be really careful to make sure that our models are correct and that we're doing the right thing. Actually looking at the spectra rather than just blindly accepting your MCMC outputs is really important because we think that we would have maybe noticed that the cloudy fit as clear was wrong by looking at those deviations that Jessica pointed out in the spectrum. We also didn't have chi-squared values for any of our fits, so we're hoping that that kind of extra information in the real case might also be a flag that you're doing something wrong and you need to go back and check your assumptions. And finally, really understanding the degeneracies from your model is going to help with all of this. So if you don't know what degeneracies are present or how your model affects the spectra, it's going to be much harder to draw any of these conclusions. And the big takeaway message, clouds are really important. So if anyone's still awake at the end of that 2-hour session, we will take any questions now. So once we had put the clouds in, that became a free parameter. So actually, the clear fit with a clear model had clouds as a free parameter, but it fits it to a very low cloudiness. So I think you'd be fine, you can't pick a random number and fix your cloudiness to that, but I don't think anyone would try and do that anyway because it would seem too arbitrary. So I think you'd get away with it. Yeah.
Thank you.